Okay, I think we are going live in 3, 2, 1. And we are live. All right, everyone. It's very nice to see everyone join here today. We are trying a different format today, so I will get into that in a bit here. But first of all, welcome you all. Thank you for joining SJAA on our guest speaker talk series. This is something we do every month on a full moon weekend because we have our board meeting on full moon weekends, mostly because we can't do much observing on that weekend. And then following the board meeting, we typically have a guest speaker come in and give a talk. And since the pandemic started, we have moved this series to be virtual. And I was just talking to Jessie before we got started that it's definitely allowed us to reach out to folks in and out of Bay Area, and that's actually the huge advantage of going virtual for this series. So one thing we are trying differently tonight is that we are letting people who have RSVP'd on Meetup join the Zoom session directly instead of having to watch on YouTube. This allows us to have a more interactive session. So everyone who is in the Zoom session, welcome. Thank you for joining. And feel free to type your questions in chat during the talk. Or if Jessie wants to stop in the middle to give some time for questions, I'll leave that up to her, how she wants to run it. I mean, given the virtual format where sometimes everyone tries to talk at the same time, we were trying to do this thing where like we were just keeping Q&A to the end. But if you have a question, just ping me in chat and I can definitely call your name and have you ask the question then. So we can work it out that way. Apart from that, regular Zoom etiquettes, I guess. Keep your video on if you could, please, so we get the live audience feel to it. Keep your microphones muted unless you're going to speak to ask a question. And that's about it. And now coming to SJAA, like Rob just reminded me that we have had Jessie as a speaker a long time ago. And I guess I just found out that it was before my time at SJA, like about 10 years ago. So we have been definitely around for a very, very long time. And we are very active club here in San Jose Bay Area. Before the pandemic, we had a lot of events, like we would always have an event happening every weekend. But we're trying to do some of those virtually right now. So we have a solar observing event. We had our star parties that we have tried to do virtually, not every month, unfortunately, but like we are trying to do them every 2 or 3 months. We are calling them armchair star party because you get to sit in your armchair at home and just watch this sky on your screen. So that's been a big hit. So it's our way of keeping the astronomy going and keeping the astronomy community connected, so to say. So if you have any other ideas, any feedback, any questions, feel free to reach out. My name is Sukhada. Sorry, I should have introduced myself in the beginning. My name is Sukhada. I'm on the board for SJ. I'm also the guest speaker coordinator for this program. And we have, like I said, about 9 board members and some officers and other program leaders who are actively running the club right now. So we're always looking for help as well. So if you want to help out in some way, if you're interested in some program, feel free to reach out about that as well. And we would appreciate that very much. Now, coming to today's talk, I'm really thrilled to have Jessie. I mean, in my mind for the first time, because was not, unfortunately, missed her last talk, because I had followed the Kepler mission closely. Like exoplanets is something that's always appealed to me. And I think we had a talk on Kepler mission at some point just after it launched. And Jessie is somebody, Jessie Christiansen, sorry, I tried, but she's somebody who has won a medal for her work on this Kepler mission. So that's really impressive. and she's currently working at NASA on a different project that she's gonna talk to us about today. And she had requested that I send her names of some fictional planets that you all might be interested in too, or that might be just your favorite. So hopefully we get to hear about those today. And with that, I would ask Jessie to start the talk. Thank you, Jessie.
No worries. Thank you so much. And I was really excited to get the invite to come and talk again, because I remember 10 years ago next month coming to San Jose. I lived in Mountain View because I was working at NASA Ames. So it was just down the road and getting to talk to the club. And it was really wonderful. So I'm glad I get to be back, virtually speaking. You know, as Sukata said, I've given many more virtual astronomy club talks in the last 12 months than I previously had, but it's very exciting that, you know, I get to talk to so many people about this. Tonight's talk is called Truth is Stranger Than Science Fiction, and it's about exoplanets. So as we said, this was something that the Kepler mission, the NASA Kepler mission, spent a lot of time searching for. So I'm going to talk a little bit about that. To open up though, what are exoplanets? Exoplanets are planets around other stars. And so let's get started. I see Tatooine in the chat. You'll be very thankful to hear that Tatooine is already included in the talk. So yes, as Sukata said, I like to personalize this talk for the club that I'm talking to. So I asked for your favorite fictional planets. And the idea is my job at NASA is I am the person at NASA who keeps track of what exoplanets we found. So NASA has an exoplanet archive where we keep track of all of the planets we found, all of their parameters, what stars they're around, all their stars parameters, anything we know about them. So I'm the lead of the team that does this, that keeps track of all these planets. So I love to hear about new fictional planets and then just do a deep dive into our archive and like find the closest equivalent. Like, have we found anything like that? And it's so fun to find out what we found because, you know, as the title says, you know, nature is even more imaginative than we are. You know, we think we've come up with some cool new thing, and then nature is like, but what if there was a black hole? So let's go into the talk. Okay, so if this was a live talk, I would ask for a show of hands who recognizes this. I see there are some videos on. Does anybody recognize this? Maybe this would help. This is Vulcan. This is Spock's home world.
Oh, yeah.
From Star Trek. So, of course, astronomers being astronomers and being unable to give anything just one name, Vulcan is also known as Vulcanus A2, Navasa 2, or 40 Eridani A2, 40 Eridani. This is because astronomers are incapable of naming anything once. But this is Vulcan. This is one of the classic science fiction planets. Let's get this going. Okay. So let's take a little brief trek through history. How did we get from science fiction to the science that we're going to be talking about today? So more than 2,000 years ago, the Greeks were talking about this idea of exoplanets. They were talking about whether or not Earth was single or plural, whether there were many Earths or just one Earth. And in fact, Plato and Aristotle argued that Earth was unique, that there would never be anything like Earth. Now, of course, they being Greek philosophers, they were doing it in this purely hypothetical thought experiment way. Like, you know, they still didn't have a good idea of what stars were at that point, but they understood the idea of Earth as a concept. And they were like, are there other Earths? So it's over 2,000 years before we really started to make progress on that question. Okay, in terms of science fiction, the first time we really start to see imaginings about the planets in the sky and maybe even exoplanets is in 1300. So Dante's Paradise explores this idea of concentric spheres around the Earth, each one being a planet, Mercury, Venus, Earth, Mars. And, you know, and that they have different ideas and stories and personalities and all this kind of stuff. Like at this point, they're already named after Greek gods. So you've already started and Roman gods, you've started associating character traits with these objects. So you've started to fictionalize them and make stories. So we've been doing this for thousands of years. Okay, let's jump forward to the Renaissance. And this Italian mathematician, Giordano Bruno, has this quote that I like from. So the Renaissance was a fantastic time in literature, in art, in science, in the Western world. It was a big revolution. And this is what he said. There are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets of our system. And I'll leave it as an exercise to the reader to work out which 7 he was talking about. So he's like, okay, the sky is full of stars. Our sun has a star. Our sun has planets. Why wouldn't the rest of the stars have planets too? He's like, there are planets everywhere. He thinks the story's done. Planets everywhere. He was actually burned at the stake for saying that. I mean, he said a lot of other very silly stuff about the church at a time when it was bad to say very silly things about the church in Italy. But one of the things he was burned at the stake for was claiming the plurality of worlds, that there were other Earths. And this was very much against the Catholic doctrine of the time. So this is the Renaissance. Okay. In science fiction, what we see is a real boom in the 1700s of the moon being this mythical place where stories would be set. You see all these stories and legends and tales set about the moon. The moon just, it takes place in the culture. That's the zeitgeist of the moment, is let's make up stories about the moon. And then 100 years later, it's Mars. This is when they start to see the canals on Mars, and they're like, ooh, what could be on Mars? So you start to, like, Martians start to be a thing that you're going to tell stories about. So Mars has its moment. In terms of science, we move to the 1900s, and astronomer Otto Struve comes up with this idea, and it's a bit of an out there idea, and in fact everybody basically rejects it. But he was like, maybe there's a way to detect these planets around other stars if we could measure the velocity of the star, because the planet will be pulling the star around same way Jupiter pulls our sun around the center of our solar system, and we might be able to see the velocity shifts. So astronomers had already seen this for binary stars, 2 stars going around each other. If you actually just measured their spectra, if you took their light and spread it out over many wavelengths, you could see that sometimes the spectra were red shifted and sometimes they were blue shifted. So the stars coming towards you and going away from you, and coming towards you and going away from you. So they knew this happened for binary stars. And he's like, well, if you took one of those stars out and put a planet in, maybe we could detect that. The problem was you'd need to have a planet right next to the star. These binary stars had very short periods, like a few days. And that just seemed pretty different from our solar system. So Mercury has a period of like 88 days, which is the shortest period planet in our solar system. So the idea of a planet having a period of like 2 or 3 days, everyone was like, go home, Otto, you're drunk. So that didn't really get much traction. Between 1952 and 1995, that paper has like 9 citations. Nobody really gave it any attention. All right, in fiction, things really start moving to the screen. Someone in the club mentioned Belus and the planet Zyra. This is when worlds collide. This is one of the very first time you see an exoplanet, like a fictional planet that's orbiting another star, on screen, is in this movie, When Worlds Collide, which came out in 1951. The first time you really see this on TV is in Doctor Who, which I'm going to come back to later, which is absolutely one of my favorite shows. You might recognize the planet in the bottom right if you're a Doctor Who fan. I'll come back to that too. But yes, so Doctor Who starts to explore, as a matter of course, fictional planets around other worlds. And this is, so far, let me clarify, we haven't found any planets around other worlds. In 1963, we don't know of any planets around other stars. We only know of planets in our solar system. But we're already making up all of these mythical worlds. All right, 1995, 25 years ago, we finally find, after thousands of years of thinking and planning and imagining, we finally find our first real planet around a star like the sun. So in 1995, we find 51 Peg. It's a planet that orbits its star in just a few days. So Otto Struve, with this technique that he suggested, he was right. These planets existed and you could find them using the technique that he suggested. So very interestingly, this paper, which I said, between 1952 and 1995 has like 9 citations, since then has like 100 citations, as everyone is like, oh man, he really saw that coming. So I just really like that story, that he was finally proven right after many decades. Okay. So as I said, my job is to keep track of all of the planets that we found, which means that every week I spend some time putting new planets in the archive. So about 18 months ago, I was putting in this new planet, HD 26965b. And I just want to start by apologizing. Astronomers give things too many names, and they give too many things rubbish names. Astronomers should not be allowed to be in charge of naming things. So this planet, HD 26965, is going in the archive, and you can see the star has a whole bunch of different names. And I'm just entering all of these, we call them aliases. These are all of the different catalog names. You guys are familiar with this. Bright stars in the sky have a bunch of different names. And one of the names pops out to me. It's 40 Eridani. And I stop and I'm like, 40 Eridani? Why do I know 40 Eridani? And then I was like, wait, are you kidding? So I go to like Memory Alpha, which is the Star Trek online Wikipedia, and I'm like, where's Vulcan? This is the star that the fictional planet Vulcan is around. I was so excited. I'm such a nerd. This is like my dream job that I get to do this. And I found that there was a planet around the star that Vulcan is around. Now, the planet that we found is not like Vulcan, not like the planet in the TV show. Here is a very, very high resolution image of the 40 Eridani system. So it's got 3 stars, 40 Eridani A, B, and C. So here's 40 Eridani A, which is the one that has a planet around it, which is very exciting. Now, the planet itself is another one of these very hot, like gas giants. So, you know, it's a very big planet that's a very different temperature from Earth. So it's around the star that the fictional planet Vulcan is around, but actually it's not very Vulcan-like. It's not a rocky planet like you see, like that picture that I showed at the start with this like a red world. It's not a rocky planet. It's a gas giant. But one of the things we have found in our exploration since that discovery of the first exoplanet is that often planets are in multi-planet systems. So the fact that our solar system has 8 planets is not a surprise, because when we look out there, what we find are many systems with multiple planets. So this the system that we found with 1 planet so far may have more planets in it that we haven't found yet, and one of them might be rocky, like Vulcan, which is very exciting. Okay, here is an artist's impression of a rocky planet that might be something like Vulcan. Every picture of a planet that I'm going to show you is either from a TV show or a movie, or it's an artist's impression of a planet. We don't have any real proper resolved images of planets yet. We do have images of tiny, tiny blobs of light, but we don't have any resolved images yet. So I'll start by saying all of the images you'll see are fictional in some way. They're either a made-up planet, or they're a made-up imagining of what a real planet might look like. Here's an imagining of what a planet that's similar to Vulcan might look like. Okay, so I was pretty excited about the Vulcan thing. So I went to Memory Alpha and I went through every single planet that has ever been visited in Star Trek. And this is up until 18 months ago. So it doesn't include Picard and it doesn't include Lower Decks, if for the Star Trek fans out there. But there are 938 planets that are in Memory Alpha. So I went through them all. And I tried to identify which ones were around stars that really had real names. So there were 51 planets that orbited stars that I could map to a real star in the sky, like Alpha Taurus or Altair or Canopus or something like that. If the star had a real name, or sometimes I gave it a little bit of leeway, like if it was Taurus Alpha, I was like, okay, Alpha Taurus is a real thing. I'm going to say that's a real star. So there were 51 real stars in our sky that in the Star Trek universe had fictional planets around them. 7 of those stars in our world have been found to have planets around them so far. One of them was 40 Eridani, obviously, has Vulcan around it. But there are 6 other stars that match between our world and the Star Trek world. And one in particular I want to talk about is very cool. This is Tau Ceti. So Tau Ceti, you know, it's got a name that you probably think, oh, I could probably see that with binoculars, and you can. In the dark side, you can probably see it with the naked eye. It's a star that has 4 planets around it that we know of. Here's the constellation Cetus. I specifically put this in for the astronomy clubs because you guys actually can read these. And so here down here is Tau. So here's Tau Ceti. This star here, this star, you go look at it, has 4 planets around it. That's so cool. You can just look up the sky and be like, that star's got a bunch of planets. And then one of the cool things about Tau Ceti is 2 of the planets are near what we call the habitable zone. So here on the bottom, I'm showing our sun. This is the model of our solar system, Mercury, Venus, Earth, and Mars. And this green shaded region is what we call the habitable zone. That's where if you took the Earth, like a rocky planet with a thin atmosphere, and put it in the habitable zone, you could have liquid water on the surface. That's basically it. That's like the set of requirements. If you put any other kind of planet, for instance, the moon or Mars, in the habitable zone, it's not necessarily habitable. Like the moon is not habitable, even though it's technically a rocky planet in the habitable zone, because it doesn't have an atmosphere. It has no way to keep the water on the surface. The water would just all evaporate out into space. So Tau Ceti has 4 planets, and 2 of them are very, very close to the habitable zone. What that means yet, we don't know. We define habitable by life on Earth, which is kind of restrictive, but until we find other kinds of life, it's kind of what we have to go on. So I would posit by saying, you know, it's life, Jim, but not as we know it. They're near the habitable zone. They're not in the habitable zone. So if there is life, it's different from our life. In some way it operates differently. It doesn't need liquid water, or maybe it doesn't need an atmosphere. There's something different about it. But that's Tau Ceti. In the Star Trek universe, it has 4 planets. And in our world, it has 4 planets. So cool. Okay. This is another planet that you guys named that you were super interested in. Altair IV. This is another one from the Star Trek world. There's not a lot of information about it in Memory Alpha, except that it orbits Canopus, which is a star I just name checked. Bright star, you can go out and see it. It's an old favorite. We haven't found any planets around Canopus yet. Wait, I might be mixing this up with another one. It might be Dune that's around Canopus. All right, let me just say Altair IV. There's not much information about it yet in Memory Alpha, but I did go and find something as similar as I could, which is HD 219134. So here's Cassiopeia. Here's the star HD 219134, and it has a planet around it that's kind of, roughly similar. So Altair IV, clearly there's 4 planets in the system. So I found a system that has at least 4 rocky planets in it around a kind of bright star. So HD 219134 is the closest I could find to Altair. I think we get to Canopus later. I think that might be June. Let's get there. A lot of these I added at the last minute, so I apologize if I trip over some of them. Okay. So let's get to the Hooniverse. So as I said, I'm a big Doctor Who fan. So if you, dear listeners, had a box that could take you anywhere in time and space, where would you go? Where do you think this big blue wedge is on this pie chart? Where does the Doctor spend most of their time? On Earth. That's kind of a bummer, but obviously the BBC budget being what it is, they have to film where they can. Most of the time, the Doctor's on Earth, probably visiting the period during which the BBC was filming a different historical thing that week. Hey, here's a bunch of Roman legionnaires' costumes. Go film in Rome. So yes, most of the time, the Doctor is actually on Earth. A goodly fraction of the time, the Doctor is somewhere that is basically Earth, maybe with a yellow filter over the front. But basically like Earth. It's lush and green, and there's blue skies and there's flowers and there's people breathing the air. It's Earth-like. The next biggest fraction is Earth-ish. Now, I put this here and I kind of laugh because this is the truth is stranger than science fiction part. Doctor Who's been going for 58 years, 3/4 of the time, 7/8 of the time, the Doctor is somewhere that's basically Earth. Just a rocky planet with an atmosphere that you can breathe, that has an outside and a sky, and maybe has caves, and maybe has poison lakes or something, but basically it's Earth. So that's super cool. But also try some more things, Doctor Who. It's one of my favorite shows, but let's get more interesting. A very small fraction of the time, they genuinely do go somewhere properly uninhabitable. So this figure down in the bottom right that I mentioned, people might recognize, is the planet Midnight, which I'll get back to. But this one is, it's a crystalline planet with very, very ionizing radiation from the star, which is deadly for anybody who's outside one of these special shuttles. So that's properly uninhabitable. That's not Earth-like anymore. There's no water or atmosphere. If you go outside, you'll fry. So that's good. That's uninhabitable. That's more imaginative. And that's actually part of the reason why I think Midnight is one of many people's favorite episodes. It's different. It's not just here, this is Earth with a slightly weird orchid. Sometimes Doctor Who is just in space. Those ones are fun too. And then sometimes somewhere genuinely different, like an asteroid belt or something getting destroyed around a black hole, all those kinds of things. So this little tiny yellow slice here is kind of the most interesting part of Doctor Who for me. Like when they go to somewhere that's genuinely different and unexpected and like properly cool in some way. And I want to shout out to JJ Eldridge, who provided me the spreadsheet with which I made this pie chart. Okay, so let's talk about Midnight. So Midnight is this crystalline planet. The whole surface is just these crystal structures. This that I'm showing you here is a schematic of a planet called 55 Cancri E. So 55 Cancri, you know, that's something you can see with naked eye or binoculars at a dark site in the constellation Cancer. It has at least 4 planets around it, B, C, D, and E. We start with B because the star is implicitly always A. So B, C, D, and E. So it's got 4 planets around it. And 55 Cancri E is a rocky world that's right next to the star. It's very short period, around a day. And the thing is, if you take this carbonaceous rock and put it under very high temperature and pressure, it's getting squeezed. The gravitational tides from the star are squeezing it, and it's very hot. What happens to carbon when you squish it and heat it up? It turns into diamond. So one of the speculations, you know, scientists are trying to work out, like, what do the interiors of these planets look like when they're so under so much pressure and radiation from their star? And one model is that they have this crystalline layer, like this, you know, the headlines were like, "Eat your heart out, Tiffany's biggest diamond in the universe," like this crystalline carbon layer under the surface. The surface is like molten because, again, it's a rocky planet right next to the star. So very, very lava. But underneath that, there's this crystalline layer. So this is as close as I think we get to Midnight, a crystalline planet, which is 55 Cancri E. Okay, another classic planet from Doctor Who is Gallifrey. This is the Doctor's home world. It's a rocky planet with multiple planets in the system. This is like one of the screenshots from the show. You can see there's this planet, there's some other planets, maybe a moon, and there's 2 stars in the background. And we have actually found a system that has 2 stars and 3 planets. And so that's very exciting. This is actually a Kepler find. So we have found something Gallifrey-ish. None of these are actually rocky habitable zone planets. But again, if you find a system that has some planets, some of them might be rocky in the habitable zone. So we did find something Gallifrey-ish. So I mentioned that last one especially was a Kepler find. So let's talk a little bit about Kepler. Kepler is the spacecraft that NASA launched in 2009. It operated as its original mission for 4 years until 2013, and then it operated in a second phase of the mission called K2 from 2014 to 2018. So the whole goal of Kepler was to stare at one patch of sky in the constellation Cygnus for 4 years and look for planets like the Earth. We wanted to know how common are planets like the Earth. We wanted to resolve this question that Plato and Aristotle had thousands of years before. Are planets like the Earth common, or are they very rare? And until 2009, when we launched the spacecraft, we didn't know the answer to that. Science fiction writers had busily populated the Milky Way with Earth-like planets so that they could easily put humans there. But we didn't know. We genuinely didn't know if the solar system was interesting and weird and unique, or garden variety planetary system around a star. One of the really exciting things to come out of Kepler, and this is something I couldn't have told you guys 10 years ago because we didn't know the answer yet, is that Earth-like planets seem to be common. We have had to do some extrapolation to get to that answer, which is always dangerous and it means you're making assumptions. But if you extrapolate from what we know to Earth-like planets, it seems like Earth-like planets are common. And our best current guess is that somewhere between 20 to 50% of stars like the Sun have a planet like the Earth in the habitable zone, have a rocky planet that's the right distance for liquid water. Now, if you think about our Milky Way galaxy, has something like 100 billion stars. Something like 25% of those are stars like the Sun, so that's 25 billion. So 20% to half of those is like 5 billion to 10 billion Earth-like planets in the galaxy. Billion with a B. That's so much potentially habitable real estate out there. And we know that because of Kepler. We're still working on some of the data from Kepler, but that's our current best guess. Okay. How have we gone towards finding actual Earth-like planets? So I kind of hinted at this when I said we extrapolated. Here's our progress over the years trying to find Earth-like planets with Kepler. So on this graphic, all of the stars are to scale with each other and to the same color scale and to the same size scale. And all the planets are to scale with each other in terms of size and a rough guess at color. But the stars and the planets aren't to scale. You can see that, like, for instance, the Earth here, this is the Earth, is much bigger than the sun. It's not true. So keep that in mind as we go around. So this is what we're looking for. We're looking for a rocky planet around a star like the sun. One of the first things we found, called Kepler 20e, again, I'm sorry for the names, is a rocky planet around a star a little bit smaller than the sun, but with a very, very short period. So this is a period of just under a day. So this is not Earth-like. The next thing we found was something that was the right temperature for liquid water. It had a longer period. It took longer to go around its star. The star was still a little bit cooler than our sun, but it was much bigger than the Earth. It was more than twice the size, 2.2 times the size of Earth, which means we think it can't just be rocky with a thin atmosphere, but likely has a very deep ocean of some kind, maybe water. Then we found a rocky planet that's the right temperature for liquid water. So now we have two of the three things we're looking for, but it's around a very small, cool star called an M dwarf, much smaller and cooler than our sun. Now, the reason that's a problem is we don't know if life like our life could exist around M dwarfs, because M dwarfs put out so much X-ray and UV radiation as part of their spectrum. So our sun is actually pretty quiet in UV and X-rays. It has its occasional tantrums, but most of the time its energy is coming out in the optical where we see it, which is maybe why we see it. That's another topic. So M stars have a lot of their energy coming out as this high energy radiation, which is bad for DNA, right? Like the reason we put SPF 50 on when we go outside is because UV is bad. And the reason that the dentist makes you wear the lead apron when you get the X-rays, because X-rays are bad. You don't want too many. So it might be that rocky planets around these kinds of stars are completely sterilized by the high energy radiation. And maybe not, life like we know it never develops. So we don't know, but this is something we're really actively thinking about right now, because it seems like these small, cool red stars, which actually make up the majority of the stars in the Milky Way, are really good at making rocky planets. So if they're habitable, that means there's even more habitable real estate in the galaxy. And then finally, we have a star like the sun. We have a planet that's the right temperature for liquid water. And it's just a little big. So this is about 1.5, 1.6 times the size of the Earth. So, 50 to 60% bigger. And that's kind of on the edge where we're not sure if it's rocky or not. We're not sure if it's some kind of water world or some other ice-rich world like Uranus or Neptune, or if it's a big rock. So we don't know. It's got like a 50-50 chance of being rocky. The main problem with this one, Kepler 452b, which you might have heard of because it was the best thing we found, is that it might not be there. The signal that we see in the data looks a lot like a type of noise that we see in the data. So it's kind of unreliable. We're not sure if the signal is really a real planet or if it's the spacecraft doing some jinkies, which it does occasionally. So that's also a bummer. So it's like a 50-50 chance of being rocky and a 50-50 chance of being real. So this is as close as Kepler got to finding a real rocky planet in the habitable zone of a star like the sun. In terms of fictional planets, so this is Kepler 20e. This is the rocky world. It's way, way, way too hot. It's so close to its star that the surface is molten. Well, we know of molten planets in sci-fi. We have Mustafar, where we have the big fight between Anakin Skywalker and Obi-Wan Kenobi. I have the high ground. This is a lava world. It's happening. This is a molten world that's going off right now. In terms of Kepler 22b, which was this bigger world that's like the right temperature for liquid water, but too big to just be rocky, it could be a water world. It has the density. If you measure the density just on average is pretty similar to water. And so that makes you think of maybe Waterworld, the Kevin Costner movie from a long time ago. And in fact, the first water world that we found, GJ1214b, our group nicknamed it Kevin, after Kevin Costner. A lot of these planets, because they have such rubbish names, also have nicknames. So yes, GJ1214 we called Kevin because it was a water world. Okay, this is the rocky planet that's the right temperature, but it's around an M dwarf. This is the star with too much high energy radiation. Now, among you might be people who are familiar with a planet around an M dwarf putting out too much high energy radiation. Krypton. So this is Superman's homeworld. Superman comes from a rocky planet around an M star, and the whole point is he comes to Earth, and the yellow light from our star gives him his superpowers because it's so different from the light from the M star. So this is a rocky planet around an M star. So this is like Superman's home. This is like Krypton. Okay, and then finally we have Kepler 452b. This is the closest thing to a rocky planet that we have. Now, someone did mention when I sent out the request to tell me favorite planets, someone mentioned Beta Z. So this is Star Trek. We're back to Star Trek. This is the home of the Beta Zoids, like Oksana Troy. And if you see pictures of it, it's basically just Earth-like. They're walking amongst gardens and flowers. There's continents and oceans. So this is as close as we got. And again, I'm hedging a lot because we're not sure. So we haven't really found a properly Earth-like planet yet. But we found so many things that are very close to that, either slightly bigger or slightly smaller or slightly hotter or slightly cooler, that we expect, this is how we come up with this extrapolation, that we expect that Earth-like planets are common. So Beta Z is out there, we just haven't found it yet. We did find a bunch of cool stuff. This is just a cool graphic showing a bunch of the different visualizations of the planets that we found. At the very last minute, someone mentioned Tatooine in the chat right before it started. So I'm very happy to say I might have predicted that because that comes up in every single talk. Tatooine. So this is the first Star Wars, right? This is A New Hope. This is Luke Skywalker on his homeworld Tatooine, looking towards the sunset. And you know, this is the 70s, right? This is George Lucas in the 70s. This is before we'd found planets in the 90s, let alone planets around multiple stars like Gallifrey, which I showed you. So this is George Lucas just totally making up in his imagination that you could have two stars with a planet around them. So cool. This is Kepler 16. This was the first circumbinary planet we found. So this is a planet orbiting two stars. We found it with Kepler. We found about a dozen now of these circumbinary planets. So circumbinary meaning around a binary star. And one of the things I particularly like is he even got the colors right. Like, again, he's just making this up, but he even got the colors right. He didn't get the sizes right, but okay, you know, I'll give him some credit. He even got the colors right. It's a yellow star and a red star. Cool. Okay. This one I added in case we have any Marvel Cinematic Universe fans out there. This planet, which is, I'm going to butcher it, but it's an awful name, so it deserves it. Ogle 2016 BLG 0149L. It's a terrible name. This is the furthest known planet that we've found. This is the planet that is farthest away from us. It's something like 30,000 light years towards the center of the galaxy. This is using a different technique than Kepler called microlensing. But this particular technique, microlensing, is sensitive to far away planets. So this is still in our Milky Way galaxy, between us and the center of the galaxy, but very close to the center of the galaxy. We found this planet. From the Marvel Cinematic Universe, you might have heard of Vormir, which is the home of one of the Infinity Stones. The way they describe it, it's an isolated star at the center of existence. Isolated planet. So this is like, as close as we get to Vormir. It's like nearly at the center of the galaxy, and it's the furthest away from us we know, and it's certainly the furthest away from any other planets that we found. So this is our Vormir. This is our very distant, isolated planet at the center of existence. So this is just for the Marvel Cinematic Universe out there. I'm trying to hit all the franchises so that everybody's happy. I didn't miss anyone. Here's June. Okay, yes. So this was, someone asked for June. So this is, they're going to make a movie out of this, and the preview looks really cool. So this is a classic Frank Herbert series of novels called June, and the planet is called Arrakis, and it's orbiting a red giant called Canopus. So we haven't found any planets orbiting Canopus yet. I mean, we're still looking, but we haven't found any planets orbiting Canopus yet. We have found planets orbiting red giants. This is HD 212771. That's it, 212771. And it's a planet found by TESS, which I'm just about to talk about, which is a different NASA mission, orbiting a red giant star. So we have found planets orbiting red giant stars, just not Canopus yet. One kind of very cool system that we don't see as much in science fiction, but does seem to be quite prevalent in nature, is what I call compact systems. So these are systems where you have a very large number of planets packed in very tightly. It's not known of in science fiction, but it seems to be so common in nature. So this, for instance, is a graphic of TRAPPIST-1. So TRAPPIST-1 is a very small, cool red dwarf that has 7 rocky planets around it. And the longest period one of those 7 planets still has a period shorter than Mercury. So if you imagine our solar system, this has 7 planets inside the period of Mercury, before you even get to Mercury. This is another one called K2138, which I particularly want to call out because it's my baby. I got to publish this one. Exoplanet scientists get to have their own little family portraits they pull out of their wallet. This is K2138. So K2138 has 6 planets around it, and 5 of them, again, are packed in really tightly, really close to the star. Now, the way these systems work, the way they're dynamically stable, the reason you can cram so many planets in is because the periods are all related to each other in resonance. So we have resonances in our solar system as well. So for instance, the Galilean moons of Jupiter, 3 of them are in a 1 to 2 to 4 resonance. So the periods are locked with each other. So for every one time the outside one goes in, the next nearest one goes through twice, and then the very close one goes around 4 times. I was in there like, so you have these resonances. And then Pluto and Neptune, for instance, are in a 3 to 2 resonance. So for every 3 times Neptune goes around, Pluto goes around twice. And the thing is, when these periods are in resonance like this, they kind of lock each other. They're very stable. They just want to stay there. They don't want to deviate at all, because then they become unstable and then it's all chaos and like billiards and stuff flying everywhere. So these systems of these really compact systems that we see with all of these planets, they're really tightly locked in resonances. Now, the cool thing about resonances is that that's what music is. Frequencies and chords and notes and intervals and music are all resonances. So K231 and K2138 in particular makes this very cool song. I'm going to stop sharing and then reshare because I think I forgot to click the share sound. There we go. Okay, so I'm going to go. So K2138 plays a song. If you put a note every time one of the planets goes around its star and you relate the note to the frequency, like the period of the planet, it plays a song. So let's see if we can get this to work. This is your moment of zen. And the reason it sounds nice is because all of these planets are in a 3 to 2 resonance. Each set of planets is in a 3 to 2 resonance. And the 3 to 2 resonance is the perfect 5th interval, which in music, in Western music theory, that's the tonic chord. This is the perfect 5th interval. So this is just music. The other very cool thing about K2138 is that it was found by citizen scientists. It was found by people at home on their computers looking at data from Kepler. So my colleagues and I had started this citizen science project called Exoplanet Explorers, and we opened it up for everybody to come and look at. Before the scientists had even looked at the data, it was just like, hey, tell us what you see. And this system was found by citizen scientists. So I was super honored to be able to include 4 different citizen scientists on the paper that we published to announce the discovery of these planets. So that was really cool. And so now this is ongoing. PlanetHunters.org is the current citizen science project for people to go and hunt for planets, but it's not using Kepler data anymore. It's using TESS data. So I'm just going to end by talking about TESS. So Kepler ran out of fuel in 2018. It had run for 9 years, it had done an exquisite job, but it finally ran out of fuel. In 2018, NASA launched the TESS mission. So where Kepler is a 1 meter telescope in space, TESS, see these 4 cameras here? These are 4 10-centimeter cameras. That's 4 inches. I bet half of the people on my screen right now have a telescope bigger than 4 inches. So this is 4 like off-the-shelf 10-centimeter cameras that NASA sent to space. Now, for the people who've used a lot of telescopes before, I'm sure you can see the small telescope, we have this huge field of view. So TESS actually looks at the whole sky in 2 years. So where Kepler did one little patch of sky over and over again, looking for long period planets like the Earth, TESS is tiling the whole sky. And it took 2 years to do the whole sky. And actually now it's gone back and started redoing it again. It's in its extended mission because it finished its prime mission last year. The goal of TESS, so Kepler had a very specific goal, right? How common are planets like the Earth? The goal of TESS is to search the entire sky to find all of our nearest neighbors that have planets, right? We're going to look at all the brightest stars in the sky, all of the stars that have the most potential for us to do more observations. The problem with Kepler was, this 1 meter telescope looking very deep. Almost all of the planet candidates that we found were around stars that were too faint to do anything else with. You were like, okay, there's something going in front of that star. Cool. If the star is bright enough, there's so much more you can do. You can measure the mass of the star and start talking about density. You can examine the atmosphere of the star, of the planet rather. You can start measuring the mass of the planet and the atmosphere of the planet. So you start asking, like, what are the molecules and atoms in the planet's atmosphere? And you can just do much more characterization of the system if the star is bright enough that you can do a lot more types of observations. So TESS is looking at the whole sky, looking for planets around bright stars. And the goal is to get like a complete census of our solar neighborhood of which stars have planets around them. One thing you might not know, but I think is pretty cool, Proxima Centauri is the closest star to our sun, 3.8 light years away. It's in the Alpha Centauri triple system. Proxima Centauri has at least 1, probably 2, maybe 3 planets around it. That's our very nearest star. That's like your next door neighbor going over borrow a cup of sugar neighbor. This is our next star, has up to 3 planets around it, maybe more, but we've seen hints of at least 3. That's so cool. And so TESS is going to help us discover all of the nearby stars that have planets. So basically, I want to leave you with this idea that planets are incredibly common throughout the galaxy. It seems like every star is just popping off planets all over the place. Even our nearest stars have planets. And also that the planets that we found have been so varying and interesting and different from what we expected. And I'm just excited to see what else we find. And what else you guys find. Please go to planethunters.org, wait for new test data, and help us find more planets. Thank you. I can take questions now.
Okay, that was wonderful. I mean, I thought I got a nice tour across the universe with all the planets you mentioned, imaginary and real.
Right.
And I'm really astonished to find out that Kepler had 4-inch telescopes. I mean, you're right.
TESS.
Most of our
TESS has 4-inch telescopes.
Yeah. Oh, TESS. Sorry. So that's really interesting because I'm looking at my 8-inch right here right now. So I can kick off with questions, and then I've been looking at the chat channel, but no questions have come in here yet. So one question I have is, you showed this pie chart where excuse me, there was Earth-like planets and then Earth-ish planets. So I'm kind of trying to understand what is the difference.
Yeah. So Earth-like is genuinely just, they called it a different name, but it could have been anywhere on Earth. It's just they're walking around with blue skies and there's ground and plants and they're breathing. Like It's basically Earth, but they just called it a different name.
Okay.
And then Earth-ish was like, they tried. They, made the atmosphere slightly different so they needed to breathe, or they made it in caverns underground, or, they made it so that there was a dark purple filter and everything looks weird. Like, It's not just like Earth anymore.
Right.
Whatever they could do with their like £20 BBC budget that week. I mean, the early Doctor Who is so amazing for what they could do on a very, very tiny budget.
Oh, that's super cool.
Yeah.
Anybody else? Any questions, comments? Please go ahead. Just unmute yourself and you can ask your question. Okay, I got a question. Oh, I got a couple of questions in the chat channel. I can relay them to you. Let's see. Let's start from the top. Actually, I'm going to start with the question that came on YouTube chat because that was that came in before any of these. So let's go in the order. I don't know this person's name. It just says Data Foxy as a username. Are astronomers checking all stars for planets, or are they prioritized in some way, such as where on the sequence the star is or the distance from Earth?
Yes, no, that's a really good question. So with Kepler, we looked at a patch of sky that was, for instance, it was 10 degrees by 10 degrees. But we chose in that patch of sky 200,000 stars that we thought would be amenable to a search for something like the Earth. So we didn't look at every single star in that field of view. We chose 200,000 stars. Now, TESS is just literally taking pictures of the sky. So with TESS, we can choose which stars we analyze. And many groups out there have different science questions like, are there planets around A giants? Are there planets around M dwarfs? And all this kind of stuff. So TESS is actually enabling many more different types of science questions with the data. Other types of astronomers are using different methods, which are sensitive to different kinds of stars. So for instance, direct imaging, I mentioned early in the talk, sometimes we can get like a tiny blob of light and we know it's a planet. That's direct imaging. So you try to block out the light from the star, like if you hold your thumb up in front of the sun and look around it. Those ones were sensitive to planets around very young stars. So stars that are only millions or tens of millions of years old compared to our sun, which is 5 billion years old. And that's because those planets, they're still forming, they're still accreting, they're still collapsing. So they're still radiating out a lot of energy. So you can see they're actually self-luminous. They're still glowing, basically, with the heat of formation. So those are sensitive around young stars. So there are different kinds of stars, but I would say astronomers are basically looking everywhere they can for planets.
I see. That's cool. Matt has a question here. Thanks for the amazing talk. What kind of survey might come after TESS?
Oh, yeah. So the next thing that NASA is planning to launch to do a survey for exoplanets is called Roman, the Nancy Grace Roman Space Telescope. It's an infrared telescope that's 2.5 meters that's going to launch in the second half of this decade. I mentioned microlensing. So microlensing is this technique which relies on the fact that if you have, I'm going to try and get my line up right. If you have a star go between you and another star, it acts like a lens. It acts like a gravitational lens because, we know from Einstein that anything with mass bends space-time around it. You might have seen this analogy of like a rubber sheet with a bowling ball in the middle and it stretches the rubber sheet. So the rubber sheet curves around the ball. So space-time does that around stars. So what that means is that the background star gets magnified. It's like holding a magnifying glass over the background star. So you're sitting there watching this background star and you see it suddenly get brighter and then suddenly get dimmer again. And that's because a foreground star or a fainter foreground star went in between. Now, if that foreground star has a planet around it, what you see is a little blip on the brightening because the planet also does its own little mini brightening. So this is the kind of survey that Roman is going to do, is a survey of a 500-day stare towards the center of our Milky Way galaxy to look for microlensing events from stars that go between us and the center of the galaxy. The exciting thing about Roman is Kepler used the transit method. I didn't really talk much about that, but that relies on planets going between you and the star and blocking some of the light. So, if you were an alien civilization looking at our sun and you were lined up just right in the ecliptic, every 365 days, you'd see our sun get a little bit fainter and then a little bit brighter again. And that would be because Earth went in front and blocked some of the light.
Right.
So that's the transit method. So Kepler is sensitive to planets close to the star because the closer you are, the more likely you are to transit, just geometrically. The further away you are, the closer to exactly edge on you have to be to transit. Microlensing is sensitive to planets that are further away from the star, like out past Earth, Mars, Jupiter, Saturn, for instance. So the two methods are actually complementary. And what we're hoping is that where Kepler was able to basically give us the census of stars from the star out to Earth, planets, the census of planets from the star out to Earth, Roman will be able to complete the census for the outer solar system from like Earth onwards. And we'll be able to put the picture together and say, okay, here for the Milky Way is like a holistic view of how many planets. So that's the next survey that NASA is launching. It's called Roman.
I see. That's pretty cool. I guess we can have you back hopefully in less than 10 years. I don't want to wait another 10 years to hear about Roman next. All right. Wow, that's quite a few questions here. Hitesh is asking the next question. Can you talk a little about habitability, especially around M-dwarf stars, which are very common?
Right. I mean, you guys should have someone come and talk to the club, because that's like a whole hour talk on its own is habitability.
Oh.
And that's
Can you recommend someone? I mean,
I'll send you an email.
Send
after.
me the name. I will reach out. I mean, I would love to do that.
Yeah, for sure. So we're thinking a lot about this. So again, there's only one place we know where life is so far, which is the Earth. And there's only one thing we know all life on Earth needs, which is liquid water. Kind of basically everything does something to protect and preserve and keep liquid water. I just drove through Joshua Tree National Park yesterday and read about all of the interesting different ways that different plants and animals in the desert find and keep water. So when we go looking for life around other stars, liquid water is like our first clue that we're looking for. And philosophically, you can talk about like in what ways that's restricting us, because, you know, maybe it shows a lack of imagination. Maybe there are other, you know, chemical pathways that produce energy gradients that would create something like a self-replicating string of proteins that aren't RNA and DNA and water-based like we have. And people are like trying to come up with different kinds of like parallel kinds of life. Like what other chemical reactions in the lab react in the same way that produce and store energy that don't need liquid water. But let's say you need liquid water. So that's why we go looking around M dwarfs, because two things. One is that the stars are much smaller. So actually finding the planet around them is much easier. When I talked about the transit method, which is a planet going in front of a star and blocking some of the light, if the star is much smaller, the same size planet blocks a lot more of the light, fractionally speaking. So when we're looking for these transit signals, it's much easier to find them around small stars. So that's exciting because, you know, we can find them faster. The other important thing is that they're much cooler, so planets can be much closer to them before they get too hot. So if you think of it like a bonfire on a beach, at the start of the night, the bonfire's raging, you have to stand really far away, otherwise it's way too hot. But towards the end of the night, you kind of huddle closer as it burns down. You can get closer and not be too hot. So these planets around M dwarfs are much closer. So a habitable planet around an M dwarf has a period, like an orbital year, of like 2 weeks to a month, compared to 365 days for the Earth.
Right.
What that means is they're much easier to find again because they're so close. They again geometrically have a higher probability of transiting, but also you only have to watch for like a couple months to see multiple transits and be like, okay, yeah, we found one. Whereas the reason the Kepler survey was a 4-year mission was because we were looking for planets like the Earth, which take a year to go all the way around and then come back. So we had to stare at these stars for 4 years to make sure we caught them. Transits are actually a very inefficient way of finding planets because most planetary systems just aren't lined up the right way. They're lined up a little bit off and you never see them transit. So that's why one of the reasons why we're looking around M dwarfs. So we know that there's rocky planets around M dwarfs at the right temperature for liquid water. What we don't know yet is whether life could actually survive there. Now, on Earth, life has evolved to, you know, we find life in places you just think it shouldn't be, like very high temperature, like extremophiles in terms of temperature, in terms of acidity, in terms of radiation, like tardigrades, tardigrades, you can't kill them as far as I can tell. So once life evolves, the way natural selection works is that life can basically fill any niche available to it. If it can get liquid water, it's going to try. It's had billions of years on Earth to do this coolness and get in all of these extreme directions. The trick is getting it to start in the first place. And that's what we're not sure about on M dwarfs because of this high energy. Like if you start trying to chain molecules together, build proteins, maybe the radiation just comes down and just keeps breaking them, just keeps splitting them. So, That's the question. If you can get it started, then, you can probably get a whole variety of things happening. It's getting it started that's the problem. So that's our
Cool.
habitability around M dwarfs. We're not sure.
Okay, cool. Sandhya has the next question. What is the closest planet that has the Goldilocks attributes, and how far is it?
It's so close. Proxima Centauri, our very closest star, has a rocky planet in the habitable zone. But Proxima Centauri is an M dwarf. So we don't know. The closest planet, the closest planet that has a rocky planet in the habitable zone of a star like the sun, we haven't found one yet. That's the thing we haven't found. We haven't found a true Earth twin that fits all three of those criteria. We're still looking.
Yep. Then Jeff has the next question. Are there any satellites that will start operations soon that will give us more insight into exoplanets?
Right. So I mentioned Roman, which is going to search for more planets. But before Roman, hopefully this year, NASA will launch the James Webb Space Telescope. So James Webb is like the successor to the Hubble telescope. It's a 6.5 meter telescope that we're launching into space. One of the things it will be able to do is to really start to characterize these exoplanets in more detail by looking in their atmospheres. So I mentioned that if your planet is around a star that's bright enough, you can actually start to examine its atmosphere. You have so much light from the star, and it's super cool. So listen to this. As the planet goes in front of the star, the planet's atmosphere also goes in front of the star, and the starlight goes through the planet's atmosphere. Now, molecules in the planet's atmosphere will block light at different wavelengths. So water absorbs at some wavelengths and is transparent at other wavelengths. So basically what we do, we map out the size of the planet as a function of wavelength. And at the wavelengths where the planet looks big, that means something in the atmosphere is absorbing at that wavelength, like it's opaque at that wavelength. So for instance, if we see a planet that looks big at 1.4 microns, we're like, it's got water in the atmosphere because water absorbs at 1.4 microns. So this is how we kind of map out like what are the constituent elements of these atmospheres. And this is what Webb will do. Webb is designed in one sense, it's got many interesting science cases, but one of the things it's designed to do is to take this starlight passing through the planet's atmosphere and spread it out and like examine as closely as possible. Like, what do we see and what temperatures and pressures do we see it at? So Webb is going to be able to, is launching later this year, fingers crossed, and we'll be able to examine the atmospheres of planets in much more detail.
That's pretty cool. Let's see. Rob is asking the next question. What distances was Kepler looking toward, and what are the distances that TESS is looking at?
Yeah. So this kind of gets back to what I was saying about the size of the telescopes. So Kepler was a 1 meter telescope looking at basically doing a deep, narrow survey, doing like a pinpoint survey on the sky. So most of the planet candidates that Kepler found are thousands of light years away. Some of them are nearby because that survey cone has a pointy end that's near us, but the bulk of the planets are thousands of light years away. So TESS is doing the whole sky around us and looking at all the bright stars. So it should do, it should find all of the transiting planets out to a few hundred light years. And some of those will be very close. Like, Proxima Centauri is only 3.8 light years away. So the typical planets that TESS finds are going to be more like hundreds of light years away. And the typical planets that Kepler found were more like thousands of light years away.
Okay, got it. Can you give me 1 second? Somebody is at the door. Just give me 1 sec.
No worries. Let me look down. So that was Rob. And then Marianne says, thank you for Gallifrey. I couldn't wait to see any and all Time Lady remote episodes. Yeah, she was awesome. We needed more Time Ladies. I agree.
Well, we have run over time today, but we have so many interesting questions coming in. So I really appreciate you hanging with us.
No worries. I can keep going.
Let's see.
My 6-year-olds aren't going to sleep anyway.
Actually, Ben said we can skip his question because you have kind of answered the question already. So he messaged me separately. So let's get to Nathan's question. Can you please briefly talk about James Webb looking into the planets?
Oh, so that's what I was just talking about. So Webb is going to be able to look into the atmospheres. So the types of planets that Webb will be sensitive to, again, we haven't actually found any proper Earth-like planets yet. But what Kepler found was the most common kind of planet is actually between the size of Earth and Neptune. So in our solar system, we have the 4 inner solar system rocky planets that are like Earth size and below. Then we have the ice giants and the gas giants, which are like Neptune size and up. Neptune is 4 times the size of Earth. And in our solar system, there's nothing in between Earth and Neptune. There's this gap. But what Kepler found is the most common kind of planet is in this gap. So sometimes we call them super Earths, sometimes we call them mini Neptunes, kind of depending where they fall in this region. But it's a type of planet we don't have in our solar system. So one of the things we're hoping to discover with Webb is what kinds of planets are they? Are they big rocks? Are they little ice giants? Are they something we don't have in our solar system, like a water world? So Webb is hopefully going to help us unlock these super Earth planets. What are they? I'm really excited about that, because this was, again, this kind of unexpected thing where, you know, we kind of figured we knew how planets formed, and then we found this whole new type of planet that we didn't have.
Right. That's pretty cool. Well, let me find the next question. Marie, engaging talk. How long does it take for TESS to send photos back to Earth?
Yeah, this is really cool. So when Kepler launched, Kepler is in a heliocentric orbit. So that means the sun is in the middle, heliocentric.
Sun is in the middle. Yep.
Exactly. So it actually trails the Earth. So Earth is going around the sun, and Kepler's kind of like trailing behind on a slightly longer orbit. So Earth is 365 days, and Kepler's 372. So it's just a bit longer. So it's actually drifting away. And by the end of the Kepler mission, it was taking 8 minutes or so. So it was almost a whole AU, an astronomical unit, behind us, because over the 9 years it had drifted quite far. TESS, let me tell you about TESS's orbits, because TESS's orbit is super cool. So you have the Earth and you have the moon. So the moon takes 28 days. I just punched myself in the face. The moon takes 28 days to go around the Earth. TESS is on a resonant orbit with the moon. So we just talked about resonant orbits. So TESS is on this long elliptical orbit. So it's kind of a long, like you take a circle and squeeze it. That goes around twice for every one time the moon goes around. So it's got a period of about 14 days, like 13 and a half days. And the Earth and the moon are actually keeping TESS in that orbit. Remember how I said resonant orbits kind of lock themselves in and they don't want to move?
Right.
So that means TESS isn't using any fuel to stay in its orbit. TESS is just hanging out, and the moon and the Earth are just like, your turn, your turn, your turn, your turn, tossing it back and forth. And so unlike Kepler, which had this fuel problem where it ran out, TESS doesn't have any like station keeping to keep the fuel, to use fuel to stay in its orbit. It just stays in the orbit. The very cool thing about this orbit is for 13 days out of the 13 and a half days, the spacecraft is quite far away from Earth, which is good, because Earth is actually a bad place to be for a spacecraft. There's a lot of radiation happening, the Van Allen belts, you know, there's Earth glow. The Earth is actually reflecting light in a whole bunch of different directions. Spacecraft don't want to be near the Earth. So it spends most of its time far away from the Earth. The problem, this is getting to Marie's question, if you're far away from Earth, it takes a long time for the data to come down. So this is the key with this elliptical orbit. Once every fortnight, it swings by the Earth and spends 4 hours just like dumping the data as fast as it can. And then it swings back out and takes a whole bunch more data. And then 2 weeks later, it swings down, dumps all the data because it's right there. And then it goes out again. So the times when it's near the Earth, when it's like, that would be the worst time to be observing because of the temperature changes and the light changes and the radiation changes. It's not observing. It takes a break. It downloads the data while it's right there. So it's actually just, it's like less than a minute. It's so close. And then it goes back out. Yeah. Isn't that cool?
Pretty smart. Yeah.
That's super cool.
It's super cool.
So let's see. We still have some questions left. Thank you for being patient.
No worries.
Well, Matt has a couple of questions. So one is it possible to examine planets outside of the Milky Way?
So technically, yes. Our instrumentation isn't quite there yet. So there's a few ways that you could detect extragalactic planets. One, for instance, is microlensing, which I mentioned, which is a technique where the star goes in front of a background star. There was a candidate exoplanet event, exoplanet microlensing event in the Large Magellanic Cloud, which is a nearby dwarf galaxy that's just next to the Milky Way. If you've ever gotten to go to the Southern Hemisphere, you've probably seen it. If you're an amateur astronomer, it's very cool. Yep. Yeah, it didn't really pan out. It wasn't a high enough signal to noise detection for everybody to be like, that's it, there's an exoplanet in another galaxy. But it was kind of a proof of concept. Yes, you could see blips in microlensing curves that could be consistent with planets if you could measure it with a high enough signal to noise. So it's really the signal to noise. You know, it's very hard to find planets. We've only just been able to do it for the last 20 years. The further away you go, the harder it is. So microlensing, for instance, is one way. Transits and radial velocity, which is this Otto Struve's method of measuring the velocity, those technically would work too. You just need to have an instrument that's sensitive enough that you could see it at that distance,
right?
Which is tough. One cool thing I'll say though is we know now that the Milky Way actually eats other galaxies. The way these big spiral galaxies grow is by accreting and stripping and destroying dwarf galaxies. Like one day the Large Magellanic Cloud will be lunch. And so we know the Milky Way has done this before, because if you measure a bunch of stars, you can see that there are groups of stars that are chemically very similar. They have very similar elements in them, and they're the same age, and they're all kind of moving in the same direction, but they were like a stream of stars that's been like spread out by getting swallowed by the Milky Way galaxy, like takes this little dwarf galaxy and shreds it. But you can kind of see the evidence behind of the shredded galaxy. So we did find an exoplanet around one of those stars. So technically, originally, it was an extragalactic planet, but the Milky Way ate it. So now it's a Milky Way galaxy planet. It's been colonized. It's ours now.
Interesting.
Yeah.
And then I guess the last question of the night, and it's actually a great question to round up the meeting with. If you had $10 billion budget for astronomy research, how would you use it?
That's a good question. So every 10 years, the entire astronomical community in North America does they're called the decadal survey. So the entire field gets surveyed to say, what do you want? What should we focus on next? And this is a survey that's done by the National Academy of Sciences and NASA. And so every 10 years we get to ask exactly this question: what do you want to do next? And the big exoplanet ideas for the next decade or two, which have a $10 billion price tag. So I mentioned direct imaging, which is this way that you can have very exquisite instrumentation to block out some of the light from the star and actually look for planets. If you had $10 billion, you could build an 8-meter telescope and send it to space, and it would have one of these instruments on it, and you could find Earth-like planets, and you could image Earth-like planets, and you could get a spectrograph and take the light from that planet and spread it out and look for biosignatures, look for evidence of life. If you had a $10 billion telescope, you could build an imager and send it to space and find Earth-like planets. That's what I would do.
Wow. So I hope you can do this dream project.
Yes, give me $10 billion.
At some point soon. Sounds very exciting. So I think that's all the questions we had for the night. Thank you very much.
Thank you so much for having me.
For taking the time to speak with us.
No worries.
I'm just going to end the stream on YouTube really quickly.
Thanks, Jessie.
Thank you.